Welcome, folks, for this webinar on efficient analysis and visualization of IoT data. I'm Atul Bargaze. I am Principal IoT Architect with AWS ProServe, and I have Rohit Rangnikar with me. Rohit, would you like to introduce yourself?
Hello, everyone. My name is Rohit Rangnikar. I'm a Senior IoT Architect with AWS ProServe.
Thanks, Rohit. So before we start, let's quickly go over the objective of this webinar. In most endeavors, there is a delicate balance sought between three competing forces. You want your application to be good, solid built. You need it to be responsive, and you want to build the application without breaking your bank. You want to also make sure that the operation of your application doesn't cost too much. Now, generally, most people end up picking towards or leaning towards either making application fast and good or fairly easy, fairly cost effective to operate and good, because you don't want to sacrifice on quality of your application. So but in today's webinar, what we are going to do is we're going to show you how to build an IoT application which is both fast, responsive, as well as it doesn't cost too much to operate. And we are going to show you how to build a solid application with good application architecture. So to summarize, we are going to talk about efficient or cost-effective IoT data ingest and processing, while still maintaining the responsiveness in the visualization of the data that is being generated by IoT devices. So here's the agenda for today. We'll start off with looking at IoT devices and the data that is generated by these IoT devices. Then we will talk about efficient ingest of this data. We'll talk about processing the data that was ingested in an efficient manner and how to analyze this data. We'll then look at optimal methods of storing this data and how to visualize this data so that it feels very responsive. Rohit will talk about some recent representative IoT use cases, and he will then go over some sample architectures that can achieve the efficient processing and responsive visualization that we talked about. We'll conclude with a quick demo. So let's start with first section of our webinar, IoT devices and the data generated by IoT devices. IoT devices are powered by embedded processors. These processors are called microcontrollers or microprocessors. Now, microcontrollers are single chip compute units. They are generally simpler processors, whereas microprocessors have much more processing power. And IoT sensors generally are paired with either microcontrollers or microprocessors, depending on the processing needs you have. So the washing machines, smart locks, smart refrigerators, your factory equipment, warehouses, windmills, all these, they tend to have plethora of IoT devices. These are powered by microcontrollers and microprocessors. They are generally paired with these compute units. And then there are billions of these out there. And so these microcontrollers and processors, they are generating data. And they are generating huge amount of data. First, because of sheer number of these that are out there and the frequency at which they are generating data. These two things result in lots of data being generated by these IoT devices. Now, the data is considered a very important strategic asset by every organization. So much so, in fact, the Economist magazine a couple of years declared that data is way more valuable than oil, which was a very valuable resource at that time. I would say these days, data has become lifeblood of most companies. So the data that is being generated by your IoT devices is becoming very important, in fact, critical for your organization. So let's look at the characteristics of this data, the data generated by your IoT devices. The data that is generated by IoT devices is constantly growing because these devices, they keep sending readings or samples at regular interval, which results in data growing exponentially. Whenever you deploy new type of sensor, you are bringing in new source of this data, and increasingly new sources of data are coming online. And whenever there is a different type of sensor or different type of reading that is being captured, it generally tends to diversify the type of data being captured. Some data is being sent in probably plain text format, still others binary format, compressed format. There is a plethora of different formats, and the data is increasingly becoming diverse. And this data is being used by lots of different personas or different types of use is being put to. To give you an example, some people use this data to get notifications, while others who are responsible for maintaining factory equipment would be more interested in detecting and predicting the failure of machinery. And still others would need some reports to make strategic decisions on procuring new things. And then the data that is generated is being analyzed by all sorts of different applications, from business intelligence tools to machine learning applications, which can generate some insights. So let's look at what customers are doing with this data. We saw different types of data being generated. Let's look at what customers are actually doing with the data that is generated by IoT devices. The data that is generated in factories and industrial setting is increasingly being used to improve the performance and productivity of industrial processes. To give you an example, one of our customer, Fender, is using this data to improve their industrial processes. Remote monitoring of patient health and making sure the wellness of the patients is also becoming very important these days. And one of our customers, Philips Healthcare, is doing exactly that. Using remote monitoring of patient health and generating wellness application using IoT data. Tracking of inventory in warehouses is a very common use case. Amazon itself does this extensively in its warehouses. And you can track all sorts of equipment as well as uh, forklifts, machines, robots that are part of the warehouses. Building smart products and user experiences is also an important use case for IoT data. Smart buildings are coming up increasingly, and generally, smart cities utilize a lot of IoT data to increase the efficiency as well as manage things in an optimal manner. Now, farm equipment tend to have a plethora of IoT sensors, and uh, IoT devices and sensors are used extensively, not only on farm equipment, but in farms to grow healthier crops and increase the yield produced by these crops. And in effect, agriculture has become very high tech, especially when large scales are involved. Energy companies, especially the companies dealing with solar panels and wind turbines, are increasingly utilizing IoT devices to increase the efficiency of the energy production as well as consumption. Mobile devices such as your cars, factory equipment, farm equipment tend to have a lot of sensors on it. And our customers, such as the automobile manufacturer Volkswagen, they are utilizing these sensors deployed in these mobile equipment to generate intelligence from the data that is coming from these mobile devices or cars and other equipments. Then IoT devices are also used extensively to enhance safety and make sure that the factory floor as well as your homes are safe to do the business that you are in. To give you an example, one of our partner, Tensor IoT, came up with this solution for COVID-19 related safety monitoring, in which they are able to, using IoT devices, quickly notify about safety violations related to social distancing and um, protective equipment such as masks and gloves. Now, let's look at what customers are doing with the AWS IoT data in different categories. So, the IoT data that is being generated can be utilized in two broad categories. It can be used to increase the operational efficiency. And by that, what I mean is it can be used to decrease the operational expenditure, or it could be used to generate new sources of revenue and result in new business opportunities. And there are different disciplines and different dimensions around how you can increase the operational efficiency as well as generate new sources of energy that are listed over here. I won't go into too much of details on that here for sake of time, but there are all these fall into these broad categories. Either you can increase the operational efficiency, uh, reduce the OPEX, or find new sources of business and increase your revenue. Now, we saw IoT devices and the data that is generated by these devices. Let's look at how the data that is being generated by these IoT devices can be ingested efficiently into the cloud so that you can gather some intelligence on the data that is coming in. Before we talk about efficient ingest, let's look at some of the constraints that exist on the data that is being ingested by your IoT devices. So on the left-hand side, I have your IoT devices, which are deployed on the edge. And what I mean by edge is factories, your farm equipment, warehouses, all the places where the action is happening. And your sensors and IoT devices are deployed, and we call it broadly as edge. And then there is cloud, AWS cloud. Now, our objective is to ingest data from IoT devices deployed on the edge, at the edge, in the factories, in shops, in your homes, into the cloud. So let's see what constraints apply to this ingest of data from edge to the cloud. Now, first, there are physical constraints. There are laws of physics. You cannot send information faster than speed of light, and electromagnetic waves can travel at speed of light. So there is constraint around the speed at which you can ingest data. Then there is economics involved. Sometimes it can get very expensive to ingest data, especially in scenarios where the bandwidth availability is limited. In remote areas, this can become very significant, where bandwidth costs are very high. And in addition to that, even the availability of connectivity can be patchy. So the law of economics becomes important depending on availability of the bandwidth. Then there are laws of the land also that you need to consider. Every region in the world has regulations in place that dictate that the data generated in a particular geographic area needs to remain in that geographic area. So to give you an example, every region, Americas, Europe, Asia, and countries in them have regulations in place which require data to remain in those regions that is generated in that geographic area. Now, let's look at some of the patterns around ingest of data from your IoT sensors into the cloud. So let's start with mobile vehicles and farm equipments, mobile things, how they would ingest data into the cloud. So on the left-hand side, we have your vehicles, farm equipment, other mobile devices. These could include trucks, trailers, any other type of mobile equipment. These have lots of sensors deployed on them. These sensors talk to something called as telematic unit. And the communication between these sensors and the telematic unit is generally carried out through wired connections. So all these sensors are physically connected to a telematic unit. The telematic unit aggregates this data, and its job is to send this data to some sort of a mobile carrier operator, or either 3G or narrowband IoT or other mobile technologies, mobile protocols. The mobile carrier then sends this data using TCP/IP or standard internet protocol to the cloud. So this is how an ingest pattern would look like in a vehicle or on a mobile device. Let's talk about ingest pattern in warehouses. Now, warehouses, these are huge facilities with lots of sensors deployed all over. These sensors could be stationary, or these could be deployed on moving objects like forklifts and robots that are part of warehouse increasingly these days. These sensors, they use some sort of a local WAN technology to send data wirelessly to a gateway. Increasingly, LoRaWAN is becoming very popular to send data locally in warehouse scenarios to a gateway. Now, the job of gateway is first to aggregate data from all these sensors in a warehouse and then convert the data to a standard open protocol which can be sent over internet. So generally TCP/IP protocol conversion happens in these gateways and data is sent to cloud from this gateway. Let's look at how data ingest looks like in factories. Generally, factories have what are called as programmable logic controllers. And these programmable logic controllers, or PLCs as they're called, they capture data from all sorts of factory equipments, your CNC machines, lathe machines, conveyor belts, robots, robotic hands. The PLCs send data to an OPC UA server or a local historian. And this data communication generally happened over a wired network. Sometimes even Ethernet network is employed. You'll need some sort of a gateway to extract data from OPC UA server or a historian and then send it to cloud over internet using TCP/IP stack. Smart buildings tend to have a lot of sensors deployed. These buildings, smart buildings as well as smart cities, they communicate with something called as building controller. Generally, these building controllers are connected to these sensors either through wired network or in some cases even proprietary wireless technologies are employed. Increasingly, even in this scenario, LoRaWAN is becoming a very attractive option. You will again need some sort of a gateway in front of these building controllers to extract data and do protocol conversion and then send this data to the cloud. Now, having seen the different ingest pattern, let's look at what it takes to connect a device to something in the cloud and what it takes to establish that communication between device and the cloud and start exchanging messages between these two things. Now, the connection that we need to establish between device and cloud needs to be first secured. Then the devices that are sending data to the cloud are probably sending the data to some sort of a service. To give you an example, a vibration sensor is sending data to a service in the cloud, which is going to analyze the vibration data and notify when there is an anomaly being detected so that you can take appropriate action. Or if a temperature sensor is sending temperature reading to the cloud, there is some service which is consuming these temperature reading to either take actions on HVAC unit or notify somebody regarding temperature exceeding some threshold. So the idea is there are disparate devices sending data to all sorts of different services. So there are data producers and data consumers. Generally, a message broker is employed to broker the communication between producers and the consumers. So the advantage of using brokers is the producers, your IoT sensors, don't have to have knowledge of all the services that exist to consume that data. They could be just generating data and sending it to these brokers. Now, you send this data to on a specific topic, and then the consumers of this data, they don't have to know about the sensors. All they need to know about the data that they are interested in, and they can subscribe to the data that they are interested in without worrying about the producing sensors. So in effect, you decouple the producers and consumers of this data using this broker. So these are some of the core technologies that you need in order to establish that link between your IoT devices and the cloud. Now let's look at how AWS provides these technologies to you so that your IoT devices can send data to AWS cloud. AWS has a service called AWS IoT, which allows you to securely connect your devices, and not only connect these devices, but you can connect large number of them. You can scale them out significantly without worrying about running into scalability issues. Then AWS IoT also provides that broker, the message broker, which we saw earlier, to route the messages, process these messages, and act upon the data that is being generated by these messages. In addition to this, AWS IoT also provides you a paradigm that allows you to communicate with the cloud in an unreliable connection scenario also, right? So if you were to communicate with the cloud where the connectivity is unreliable, you generally tend to incorporate some sort of error handling in your communication. But AWS IoT provides you some construct which allow you to not worry about intermittent connectivity issues and still be able to communicate your data to the cloud. And then finally, because AWS has huge selection of services in place already to process, analyze, and generate insights into data, AWS IoT allows you to integrate with these services, which allows you to quickly derive intelligent insights on top of your data. Now, let's look at the process of ingest, process of data ingest using AWS IoT. Now, AWS IoT data ingest can happen from three different categories of devices. You can have devices that don't have anything, any artifacts that are related to AWS IoT and still be able to communicate with AWS IoT, because all the interfaces of AWS IoT are open standards. If you are able to talk over MQTT and are able to secure your connection using X509 certificates, you should be able to talk to AWS IoT without having to put any AWS IoT construct on these devices. And these can be categorized as your third-party devices. Then if you're building new devices, it makes sense to use AWS IoT SDK, because the SDK provides abstractions so that you can easily establish connectivity with AWS IoT and send data. Then if you have a need to use some sort of a real-time operating system on your sensors and IoT devices, you could leverage Amazon FreeRTOS, which has built-in connectivity module with AWS IoT. In case of factory setup, you'll generally have your OPC UA server or historian generating the IoT data. And these also can be made to talk to AWS IoT. So you can have your the three categories of devices talking to AWS IoT directly, or you could have this communication through some sort of intermediary if you have some sort of a local network, right? So the IoT devices could be talking to a gateway over local network. And this local network could be Wi-Fi network, it could be LoRaWAN network, it could be a proprietary local network. The gateway can run another AWS service called AWS IoT Greengrass, which simplifies the communication with AWS IoT. And then the gateway in turn can talk to AWS IoT over MQTT protocol. In case of factory equipment, there is yet another service called AWS IoT Sitewise, which could be deployed on Snowball Edge, a hardware device from AWS, or it could be deployed on other hardwares. And then AWS IoT Sitewise can communicate with AWS IoT in the cloud. Now, let's dive a little deeper on the connectivity aspect of AWS IoT, what it takes for your IoT devices to connect to AWS IoT in the cloud. So the first thing you'll need is you'll need to register your device with AWS so that AWS is aware of these devices. Then you'll need some sort of security keys so that your devices are properly authenticated. Now, these security keys can be either generated by AWS IoT or you could bring your own security keys, but you'll need some sort of security keys to authenticate your devices. And then finally, you will need to associate a set of permissions which dictate all the things your device can do. Now, let's dive even deeper and look at some piece of code to see how the connectivity from your devices to the cloud can be achieved. Now, the first thing you'll need is you'll need to import some dependencies. And in this case, we are importing AWS IoT device SDK here. And then you need to instantiate a device object from the SDK and pass it some parameters to establish the connectivity. Now, there is a version 2 of the SDK available, but I'm using version 1 of SDK to demonstrate the configuration of connectivity to keep things simple. But version 2 SDK also should look similar. All the aspects around registration, keys, and permissions should look exactly similar. The first set of configuration you need to pass to the device object of AWS IoT is authentication parameters. And these are your X509 certs or keys that you have either generated yourself or you have obtained from AWS IoT. Then you need to specify a unique ID for your device. This is MQTT specification. Every device need to have a unique client ID. You also need to specify the protocol, and AWS IoT supports multiple protocols. You could use to AWS IoT using MQTT, WebSockets, or HTTP connection. And finally, you'll need to specify the endpoint to which you're going to talk. every AWS region has a unique endpoint, and you need to specify that endpoint here as a configuration parameter. Now, once you have established the connection using these configuration parameters, let's look at what it takes to ingest data into AWS IoT. Now, the first thing you will do is package your payload or the message that you want to send into some sort of some construct. Here we are using JSON, JavaScript object notation objects to send the readings, revolution per minute and current consumption readings to AWS IoT. And then once you have packaged this information in a string, all you need to do is publish this information to a topic, an MQTT topic. So in order to send this data to AWS IoT, you need two things. You'll need an MQTT topic that dictates where you are sending this data, and you will need the actual payload, the actual content of the message being sent. Having looked at details around connecting to AWS IoT, let's look at how do we process efficiently the data that is being ingested and then optimally store and visualize this data. I'm going to walk you through some patterns around efficient processing or some strategies around efficient processing of ingested data. And then Rohit is going to talk to you about some of the strategies around optimal storage and visualization of this data. So let's look at what are some of the strategies for efficiently processing data. First, you can process some data at the edge even before you send this data to the cloud. And with this, you can first reduce your data considerably. If you don't need to send every reading to the cloud, you could only send reading which is relevant. You could compress data. You could encode data if you need to transform it in some format. You could also aggregate this data. You could do something called as delta encoding. By that, what I mean is you could send data only when there is change in reading. So, for example, if you are sending temperature reading every minute, you can send temperature reading only when the temperature changes. And these are some of the strategies you can use to process your data at the edge to make your processing more efficient. And you can employ AWS IoT Greengrass to do this processing at the edge. Then you could use a service in AWS IoT called AWS IoT Core Basic Ingest. And this service allows you to efficiently ingest large amounts of data without incurring the messaging costs. The caveat of this is you cannot utilize the broker functionality, the publish and subscribe broker functionality. So if your objective is to just ingest data, large amount of data efficiently, then you can use IoT basic ingest, and that can save you a lot of money if your needs are simple ingest of large amount of data. And in order to do that, you have to use special topics starting with $AWS prefix. And you can send this data to AWS IoT basic ingest and save on the messaging costs. Then another strategy you can use is to process data in batches. So instead of doing busy processing on very small packets of data, you can aggregate the data into batches and then efficiently process this data by windowing this data and then processing quickly this data using aggregation of these events. The next strategy you can employ is you could use event-driven architecture. So what I mean by event-driven architecture is instead of polling for data constantly, you could fire events, Lambda, Lambda actions in response to important events, and then quickly process these events. The next strategy you can employ is use what is called as Lambda architecture. And what I mean by Lambda architecture is combine the batch processing and the event-driven architectures so that you come up with this cold path and hot path. And you would generally have a cold data store as well as hot data store. And we will see these, Rohit is going to talk in detail about some of these later on in our webinar. But this Lambda architecture is increasingly becoming very popular for efficiently processing data that is generated by IoT devices. So with that, let me pass it to Rohit to talk to you about some of the trends in data processing. Rohit?
Okay, before we talk about how to take advantage of data, let's first talk about three major trends that impact the way you think about data. Atul just spoke about the trend depicting an explosion in data by connected smart devices such as mobile phones, cars, smart home devices, and others. And also applications are generating real-time data such as, let's say, purchase transactions from e-commerce sites, user behavior from mobile apps, and also tweets and posts from social media. So one of our estimates is that data grows about 10x every 5 years. So I'm going to talk about two other trends that we see in data processing. The second trend that we see is that applications are being split up into microservices. So organizations are moving from the development of monolithic applications into a more microservices architecture. What that helps organizations do is that it lets them break down a complex problem into a number of independent units so that developers can then operate in small groups and respond much faster to changing requirements. The consequence of that is that when you break an application down into independent pieces, you tend to pick the right tool for the job. So in this case, developers pick the right storage, processing, or visualization components for the architecture that they're building. And the other consequence is that analytics is now at the forefront of every application that's being built. You need to know what's going on in your business and in your application in real time. The third trend that we are seeing is that there's a rapid change that's driven by DevOps. And as we innovate quickly, businesses are transforming traditional IT into the DevOps model. And this model uses an automated process for continuous development, deployment, and improvement of software. It also introduces a very fast rate of change through the lifecycle. And as you think about designing your data and your data platform, you also need to think about the operational aspects of your architecture. So let's move on to how customers are utilizing these services. So what we're seeing is customers are moving to more fully managed services. What this means is that these services automate the undifferentiated heavy lifting and allow you to focus on the business problem rather than the monitoring and the patching that's common with traditional applications. Customers are also building modern applications with purpose-built services. So gone are the days when you would use a single general purpose database for driving both a web application and using the same application for long-term marketing reports. And the third one is that moving away from, say, legacy storage and processing frameworks, where there's significant resources needed to maintain, manage, and license those frameworks. So we're going to look at these points in a little more detail. So fully managed services on AWS, what these do is they automate the undifferentiated heavy lifting. Let's say in this example, I'm taking the example of databases. If you were to say do a self-managed database, you would have to do, besides the schema design, the query construction, and the query optimization that you do yourself, you would also need to deal with the backup, recovery, the security, the compliance, the monitoring, the patching, and all those other components that go along with it. But if you were to use a fully managed solution, you would be focusing on the business application that you need to worry about for your own architecture, and you would leave the rest of it to AWS. So let's look at some modern application requirements. There are a number of factors which contribute to, say, the performance, the scale, and the availability of modern applications. So in today's environment, user growth is a very common KPI for businesses, and the cloud's global footprint enables businesses to touch new customers. This means that your application needs to support millions of users generating or consuming terabytes and petabytes of data globally. At the same time, users and businesses expect a stellar experience on your application. So API calls should return in microsecond latency while supporting virtually unlimited devices generating or consuming an unprecedented amount of throughput. And businesses, in particular startups, they cannot invest millions of dollars in hardware and licenses upfront. Instead, what they do is they hedge their success by paying only for the resources that they consume. Consequently, developers approach applications and storage in a way which is decoupled from each other, and where each component can be independently scaled. So let's look at what developers are doing to meet these modern application requirements. So they're breaking these complex applications into smaller pieces. This is where we talked about breaking a monolithic app into microservices and picking the right tool to solve each problem. When you break each application down into smaller pieces, each app itself can be well architected, and it allows each app to scale effectively and independently. Developers are also building highly distributed apps using a multitude of purpose-built services, and we'll see some of these in the scenarios that we outline in the rest of the presentation. So jumping into some database and storage services, these are some of the ones I've highlighted with an IoT focus. So in the case of relational databases, something like RDS and Aurora, organizations primarily use these for managing relationships between entities. So you may have an inventory system which has relationships, or an order processing system which has transactions, and that's where relational databases really shine. On the other hand, you have non-relational stores. So for example, if you're storing key value data at internet scale with millisecond latency lookups, you might want to consider something like DynamoDB for those applications. You might need an in-memory data store for caching and real-time workloads where Amazon Elasticache could be used. Or you might be building an application with highly connected data, and you could use a graph database like Amazon Neptune. Additionally, I've also included Amazon Elasticsearch and Elasticsearch Service and Amazon S3 as storage services, since these are widely used in search and data lakes in IoT applications. So now that we've looked at the database and storage services, let's take a look at some visualization options for IoT data. So for longer-term trends and analytics, Amazon QuickSight is ideally suited as a cloud-native serverless business intelligence service. So it allows you to build managed dashboards. It allows you to sort of quickly throw these up on the screen and connect to a variety of data sources in AWS and on-premise directly on the dashboard. In the search, monitoring, and device management space, we have Elasticsearch, we have IoT Sitewise Monitor, Amazon CloudWatch, and IoT device management, which allow you to do a combination of those capabilities I mentioned. So, for example, you could use data that's obtained in IoT device management, forward those metrics to CloudWatch, and then you can build operational dashboards in CloudWatch. You could also build dashboards in IoT Sitewise Monitor and also in Elasticsearch service using Kibana. And these dashboards are primarily used when you want to do device management, or you want to see a list of your devices that are in the network, for example. And now on the other end of the spectrum, you have custom dashboards which can be built using a number of AWS services like AWS AppSync, Amazon API Gateway, or you could build whole applications on Elastic Beanstalk or Elastic Container Service. You can also roll your own custom JavaScript frontend and then deploy those and have those connect to APIs that you've built on AppSync or API Gateway or Elastic Container Service. Okay. So now that we've talked about ingest, storage, processing, visualization, let's wrap all of this together with a concrete scenario. Let's say you are an organization that manufactures and distributes smart air purifiers. This is a hypothetical example, and the air purifiers may have a sensor which monitors metrics such as nitrous oxide, ozone, particulate matter, etc., humidity, temperature, and it reports this data periodically. So if you're an organization manufacturing and distributing these air purifiers, here are some use cases you might think of. So you might want a dashboard which shows short-term trends. So how many air purifiers are online and offline in the last 30 minutes? So you might want to put this up in your company headquarters to show what the short-term trends are. You might want a marketing dashboard showing how many unique subscribers have signed up and connected over the last 6 months. So this can show you month over month growth in subscriber base. You might want a dashboard for customer service representatives to search and pull up the status of a device. So when a user calls in, they might want to debug the root cause and do a root cause analysis of that device. So when you do a search, you can pull up the past history of that device and see where a problem might be. You might want to do a live custom dashboard displaying the health of a device for the operations team. So this might be a very near real-time dashboard showing the last reported value for a device. And you might also want to do a sort of near real-time custom analytics dashboard, so which is displaying aggregate values like a min, max, average in a geographic region. So we're going to see some portions of this in a demo. So we're going to see the last two in the demo, but we're going to cover all of them as various scenarios and how we use AWS services to build this entire platform out. So let's take a look at the first scenario. So this is a dashboard which shows short-term trends. So for example, how many air purifiers are online and offline in the last 30 minutes. So this is one approach you could take. Your devices would be reporting this state to AWS IoT core, as Atul mentioned. From there, you could use an IoT rule, and you can forward that event to AWS IoT Analytics, to a channel in AWS IoT Analytics, and you can perform an analytic function, or you can perform analysis, which then is made available as a data set. That data set can then be connected to Amazon QuickSight, and you can build a very quick dashboard in QuickSight to display that visualization. So this is a very fast approach to creating a managed dashboard using completely managed services. The characteristic is that it has moderate processing latency. So the latency depends on the kind of analytics you run in IoT analytics, and is made available for your visualization. So the processed data may be available in the order of minutes from when it was generated. And the processing data window could be in the order of minutes, which what that means is that when you generate an analytic function, you will be processing a few minutes worth of data for that window. And finally, you have very fast dashboard query response time because your data is available already for visualization in QuickSight, and the data is rendered pretty quickly when the users view it through the dashboard. So in this scenario, you have a dashboard that's built in a managed BI service, and your analytic logic can easily be modified in AWS IoT Analytics as your requirements change. So moving on to scenario number 2, this is a dashboard for data lake, which builds a dashboard on a data lake using for BI and analytics. So the scenario I mentioned earlier was you want a marketing dashboard showing how many unique subscribers have signed up and connected over the last 6 months. So your devices would be reporting the state to IoT core as usual. From there, you use an IoT rule, and you can forward that event to Kinesis data firehose, which performs batching and optional transformation functions on the data set. This transformed data would then be available in an S3 bucket, and you could then use something like AWS Glue, which is a fully managed ETL service and as well as Amazon Athena to perform those longer term analytics on gigabytes and terabytes of data, and finally storing those results back into S3. What you can do is also connect Amazon QuickSight up to Athena and have you do at runtime queries against the data set in S3. So some of the characteristics are that it uses fully managed services. Again, the storage latency is moderate. It's in the order of minutes because of the batching that we do with Firehose. The processing latency can be high because this depends on how much data you want to process. So if you're generating, let's say, a report for the past month, you need to collect 1 month worth of data to be able to process that. So the processing latency could be high depending on the volume of data that you do a processing job with. And finally, the processing data window is of the order of days or weeks or months, typically in this kind of architecture. And the dashboard query response time can be moderate. So this depends on when you run a query, when you display a visualization on QuickSight, it runs a query through Athena, and then depending on how that data is available in S3, your query response time can vary. So if the data is already been generated in a form that is displayable, the query response time can be very quick. If not, if you are doing a more ad hoc runtime query, that can take a few minutes to display. So in summary, you have a dashboard which can query the data based on the visualization needed, which is then translated into a query by Athena on the data store in S3. And in this way, when you update your visualization, you can slice and dice your data set in different ways. Let's look at scenario number 3. This is a dashboard for customer service representatives to search and pull up the status of a device and look at past debug messages for root cause analysis. So this is a very simple architecture. As always, the data is an IoT core. You have an IoT rule, which is now forwarding data to Firehose, where in Firehose, again, you can do an optional transformation function on the data set. But what Firehose would do is then it would forward the data into Amazon Elasticsearch service, where the data is available almost immediately for search and graph on the Kibana dashboard. So some of the characteristics of this solution are, again, it uses managed services. The storage latency is in the order of minutes based on the batching used in Firehose. There is no processing or very simple pipeline processing that is done in this architecture. And the dashboard response time is very fast because the data is indexed and you can limit your search query to a specific date range in Kibana, as well as also provide additional filters. So in summary, users can search the Elasticsearch index and look up records for events that have come in. And in this way, you can build a sort of near real-time dashboard for search. Moving on to scenario number 4, this is a custom dashboard that is built. So if you've noticed in the previous examples, I've used AWS services for the visualization pieces, whether it is QuickSight or Elasticsearch and Kibana. Now I have a web app that's demonstrated here with AWS AppSync, and I'll get to this piece. But as usual, the data is coming in with IoT core. You have an IoT rule, and in this case now you're using event processing to process the events that you care about with AWS Lambda. And Lambda is doing some processing or transformation on that event, but then it's persisting that event in DynamoDB. And the nature of persisting it in DynamoDB is that it's available for quick lookup for when you do the query against it. So in this case, we have users connecting to a custom JavaScript web app or dashboard, and that dashboard is connecting in an authenticated way to AWS AppSync. And a DynamoDB table is configured as a data source in AppSync. So that data is available via the GraphQL queries that you have configured in AppSync. So we will look at a form of this in the demo that we show you. So in summary, what we have is the characteristics are, it's a custom dashboard that is built. So a lot of applications which require you to build a dashboard that's very custom, and you need to build your own JavaScript or own user layout. This is ideal for that use case. There's extremely low storage latency. So the data, as it's available in IoT core, almost immediately after it's available in DynamoDB, because of the extremely low event processing time that it's taken in the path from IoT core to DynamoDB, depending on the processing and transformation that's required in AWS Lambda. And there's a very fast dashboard query response time. And this is because DynamoDB can give you millisecond lookups when you query it right. So here, in summary, we have a custom dashboard that is built by you and hosted in a number of ways. So the web app itself can be hosted on something like CloudFront and S3 using API Gateway or Elastic Beanstalk as the web app itself, to host the web server. Or you could even run the application on containers in ECS. The application then makes an authenticated call to AppSync to obtain data from the DynamoDB data source, and that is a very low latency method of access. Looking at the last scenario, this is a custom dashboard which also introduces a bit of streaming analytics. So in the previous solution, we saw an architecture which is just sending the data as it came in with low or very minimal transformation to a data store. In this case, we've introduced a pipeline in there which also has a Amazon Kinesis data analytics piece, which is doing a streaming analytics. Okay. So for example, let's say you are displaying aggregate values for the last 1 minute. So if you have an air purifier that's generating data every 10 seconds, your Kinesis data analytics could do a group function on a 1 minute interval and could take everything that came in the last 1 minute window, and it could do a group function, which could be a min, max, average, or any function of that nature. And you could then forward that event to Lambda. And the Lambda in this case is acting as a persistence Lambda, which is then just persisting the data in DynamoDB. So some of the characteristics of this solution are it's again a user-built custom dashboard. There's moderate storage and processing latency. So this depends on the window function that you use in Kinesis data analytics, as well as the batching that you do in Firehose. The processing data window is in the order of minutes. So that could be based on the window size that you pick. And it's a very fast dashboard query response time. That's because the data is already available for query when you query it through the web interface. So looking a little bit closer at the Kinesis data analytics aggregation app. So this is a small snippet of code on how you do that aggregation. So in this case, we have an input stream. In this case, we have a source SQL stream 001. What we're doing is we're grouping by a combination of the device ID, as well as we're doing a round down to a 1 minute interval. So we're rounding down to the minute level for the timestamp that comes in. And then on this data set, we're then doing a aggregation function of min, max, average, and count for the temperature values that are coming in. So this is how we're generating a Kinesis data analytics aggregation function. And you will see this in the demo as we present it. And then finally, once the data is aggregated in Kinesis data analytics, it's forwarded over to a persistence Lambda function. And in this Lambda function, you will see that there could be multiple records that come in from Kinesis data analytics. And for each payload that comes in, we're extracting an individual field, and we're extracting the individual aggregation values and persisting them in the database, in this case, DynamoDB. And then finally, wrapping this whole thing up, we are going to have a demo architecture that we're going to present to you. So this is a combination of a few scenarios that we demonstrated. So this uses a custom dashboard. It uses a streaming analytic path, as well as a cold data path. So you have a data lake in there as well. So the first component is the IoT data ingest. The second component is the real-time processing and the storage. And the third component is the data lake for BI and analytics. And the fourth component is the custom dashboard with streaming analytics. So that's it for my portion of the talk. And now we jump into the demo. Thank you very much.
Here's the architecture we are going to demo. We are going to demo 4 components of this architecture as Rohit went over. We're going to start with IoT data ingest. So I will show you data coming into AWS IoT core. Then we are going to show you the real-time processing and storage of this data. We are going to show you the data lake And then Rohit will conclude with a demo of real-time dashboard. So let's start with data ingest. I'm going to use a simulator to simulate IoT devices ingesting data into AWS IoT. So here's a simulator which is generating messages at a regular interval, and it is simulating multiple devices generating messages, and these messages are being pumped into AWS IoT core. So let's see how these messages look on the other end in AWS IoT core. So here's IoT core console in AWS. The messages are being sent to a topic starting with application. So I'm going to subscribe to all messages starting with application as starting string. And you can see here the messages are being dumped. So as the messages are being sent by the simulated IoT device, they are arriving, and the messages that are coming into IoT core are being shown over here. So we can see the messages coming in with different device IDs and the readings that they are sending in the form of temperature data, humidity data, and other related data. And these devices are sending these readings on distinct IoT topics that you can see over here. So this verifies the fact that the simulator sending data is arriving into AWS IoT and completes the first portion of our data of our demo, where we saw messages coming in into IoT core. So let's look at second part of our demo, real-time processing and storage of IoT data. Here the messages that are coming in from simulator are being processed in real time using Kinesis. There is a Kinesis analytics application. I'm going to go to Kinesis console and show you the Kinesis analytics application and the real-time readings coming into Kinesis analytics application. So the readings are aggregated using tumbling window, the code of which Rohit showed you earlier. And the readings are being aggregated, and for a window of time, which in this case is 1 minute, minimum value, maximum value, average value of every reading, as well as how many readings are being obtained, is calculated by this Kinesis application, and you can see these values being generated by Kinesis application. Now, once we have these values, the next part is to show these values being persisted in real-time data store, which in this case is DynamoDB. So here I am on DynamoDB console, and as you can see, the messages are being populated in DynamoDB in our real-time data store. So all the sensor readings from different sensors, sensor SF East, sensor SF North, sensor SF Northwest, are sending data to our real-time data store. And this concludes our real-time data store demo. Next, we will talk about the data lake. In our case, our data lake is S3, and we'll be showing the messages being dumped to a specific bucket in S3. And I will be showing you the messages. I'll be showing the files being populated in S3 buckets, and I'll be showing you the contents of this file, So here I am on S3 console, and I'm going to refresh the bucket content. And as you can see, the files are being written to into this S3 bucket. I'm going to download this file, and I'm going to open the contents of this file so that we can verify that the message readings are being populated in the file that are being generated on S3 bucket. So let's have a look at the content of the file that was downloaded from this S3 bucket. So here is the file that has the readings, and this was the file that was populated in S3 bucket, and this shows the messages getting populated in the S3 bucket. So this was a demonstration of data lake path, that cold path that we talked about earlier. So we talked about data ingest, we talked about real-time processing, we talked about cold path in the form of data lake. Rohit is going to show us the visualization of this data in the form of custom dashboard, which is going to query the data from real-time store and visualize it.
I'm going to be demonstrating the dashboard for visualizing the data coming in from the Kinesis Data Analytics Aggregation app, which is then acted on by a Lambda function and finally persisted in a DynamoDB table. The DynamoDB table has been configured with a DynamoDB stream, and if you're not familiar with DynamoDB streams, it's a feature which enables you to capture and store a time-ordered sequence of item-level modifications, such as inserts, updates, and deletes from a DynamoDB table. In this demo, we're using DynamoDB streams configured as a trigger to another Lambda function, which is responsible for publishing the data to AppSync. The reason we're doing this is because we're using an open source project, which is this project here in AWS samples, located in GitHub. We've made a slight modification to this architecture that you see over here. For instance, we have removed this piece, or rather we have bypassed this piece of the architecture, and we are using the DynamoDB stream to invoke this Lambda function directly. The Lambda function then runs a mutation in the GraphQL that's sent to AppSync, and this mutation causes the data to notify a subscription. And in this case, we have our JavaScript dashboard, which is subscribing to the event. The other modification we have made in this project is on the front end, which in this case is designed for a water pH sensor, and that has been modified for an air quality sensor. So let's jump over to the DynamoDB table and look at some of the records which are stored there. So this is the DynamoDB table that's the output from the Kinesis Analysis Aggregation app. Taking a look at one of the records in here, you see the device ID, you see the timestamp that the data is coming in at. This timestamp is aggregated to a minute level. So for every device, you should see one record for a specific minute. And then you see various attributes for that minute. So you see humidity, nitrogen dioxide, ozone, for example. And if you open each of them, you see within there's a nested structure which has the average value, the count, the min, the max for that specific attribute. So moving over from the DynamoDB table, this has a stream that's configured on it, and this stream is set up as a trigger to our Lambda function. Now this Lambda function is responsible for calling the create sensor value mutation that's defined in our GraphQL schema. So that's the part that you see over here, and this is the mutation that's called by the Lambda function when it receives an event from the DynamoDB stream. Now moving over to the AppSync console, you can see the GraphQL schema over here. So here you see the model that's defined for the sensor value. So you see the ID, the sensor ID, and all the various attributes that are associated with the data model that's coming in. You also see the mutations for the schema. In particular, you see this create sensor value mutation, and then you see the subscription, which is on create sensor value, which is linked to that mutation. Next, I will show you the sample dashboard that I have running on my laptop. And this is receiving data from the GraphQL subscription and updating the data in real time on the screen. So this is a main page showing you, all the sensors that are available, and they're sort of geolocated by data that's configured through IoT fleet indexing. Moving over to an actual sensor page, that shows you a detailed sensor view of data that's coming in for that particular sensor. In this case, the sensor ID is sensor SF North. And this panel over here shows you the live or the last updated value or the last received value on the dashboard for that particular device. The values you see below are plotted on a line chart, and this shows historical trends for the values that have come in for that particular metric. Now, the way this dashboard is designed, it's designed as a live operational dashboard. So it only plots data that's coming in as it is pushed. So if you refresh the page, it'll start again from with no points on the plot. With some changes, you can easily modify the AppSync source to use the DynamoDB table and plot the stored records as well. The other thing I wanted to show you is if you open the dev tools on your browser, you can see the payload for each record that comes in over the GraphQL API from AppSync. Here I'm expanding a specific subscription event for onCreateSensorValue, which has all the aggregated values for that interval. So that's all I wanted to show you for the dashboard. Please check out the code for any of your IoT projects, and thank you very much for attending this webinar.